So hello friends, today we are going to discuss about steady state error, which is the last parameter of time domain response analysis. The last parameter is steady state error. Now first you have to understand what is steady state error and how much important this is. So steady state error is the error in the output which you get in the steady state, right? So the error with respect to what? With respect to reference input we take. The reference input for desired output which we take minus the actual output which we get in the steady state. That is called steady state error. Means how much fluctuation or error is there. That is called steady state error. Now when we get the steady state, so normally we take t tends to infinite, means time tends to infinite, there we will get steady state obviously. So in the steady state RT minus CT, if RT is the reference input and CT is the actual output, then RT minus CT is the error, and in steady state limit t tends to infinite. That is the whole expression for steady state error. Now we are going to find out more standard equation for steady state error. But before that, let me tell one thing, that steady state error is the patent for time domain analysis. Means this steady state error parameter you will not find out in any domain, any other domain. Means in frequency domain you can't analyze steady state error. This is only specially for the time domain analysis. And in the exam steady state error is very important parameter, very important. You always have to remember the basic expressions for different type of systems, and this is very important. So now let me start with the basic expression of steady state error. So this is the basic expression of steady state error. We can write it as ESS, steady state error, that is limit t tends to infinite RT minus CT, where RT is reference input for desired output minus CT is actual output. That will give us steady state error. Now previously we have studied that the output CT will be 1 minus e to the power minus zeta omega in t by root over 1 minus zeta square into sine omega dt plus theta. This is for step input RT is equal to 1, and this is the steady state, this is the output, the step response. So we have seen the plot previously. The plot was like this. Here it is 1, means the final value. The plot was going like this, and finally it became 1 in steady state. So in steady state, the steady state error will be 1 minus 1 is equal to 0. Now this we know, but what is the general formula for a steady state error when we take any kind of system, right? Means taking GS, HS, what will be the basic standard formula when you take those? So now let us see that thing. Now taking S domain means the Laplace transform, we can get ESS is equal to limit S tends to 0 S dot ES. Now how does it come? It is quite similar to the final value theorem in Laplace transform, you will know that. So from there this equation we can directly call upon. So it will be limit S tends to 0 S into, in place of ES it will be RS minus CS, the Laplace transform of both. This will come as a formula. Now in general we have seen the block diagram, that is RS. Here is a error detector and it is going to the plant. Let's take the transfer function as GS. Finally we are getting the output CS, but here we are taking the feedback. So in this case we'll be taking unity feedback. Basically in 90% cases in the exam it will be told that take unity feedback. So I am directly taking the formula or deriving the formula taking unity feedback. So in this case HS, that is the feedback, will be 1 unity feedback. So why I am taking that, I have told you. So now let us find out the formula. So now you know that when feedback is unity and we are taking negative feedback because it will be providing more stability to the system by taking negative feedback. So CS by RS will be GS by 1 plus 1 into GS, that I am directly writing GS. So now I am taking CS is equal to GS into RS by 1 plus GS. Now I can directly put this in error equation, that is RS minus CS. So RS minus CS is equal to RS minus GS into RS. I am putting it here. GS by RS 1 plus GS, right? So this will finally give you RS by 1 plus GS. Just cross check this equation. So you will get this from as ES, means the error. So the final formula, final and also the standard one taking unity feedback, that is ESS is equal to limit S tends to 0 S into RS by 1 plus GS. This is the most standard formula for steady state error. Now we can vary this RS, means the input can be different kind of. So we are taking the basic inputs like unit step, unit ramp and also unit parabolic. In that cases, let us see what are the steady error equations. Now first we are taking unit step input. So the Laplace transform of unit step is 1 by S. We are putting that 1 by S value in steady state formula, steady state error formula. So the S term and S term will be cancelled. So it will be 1 by 1 plus limit S tends to 0 GS. We can write this like. So this limit S tends to 0 GS can be anything, but finally it can be taken as an coefficient, right? So generally in this case we take it as 1 by 1 plus Kp. Kp is called position error coefficient. So here limit S tends to 0 GS is equal to Kp, where Kp is position error coefficient. Now this is the second case. Here we are taking ramp input, unit ramp. So in case of unit ramp, RS means the input is 1 by S square. The Laplace transform of RT, that is 1 by S square. So in this case, if I take the steady state error expression, that will be limit S tends to 0 s into 1 by s square, means this is rs by 1 plus gs, is equal to limit s tends to 0, s will be there, only one s will be remaining, so that will be 1 by, I can write it like it, s plus, I am multiplying s with this term, so s into sgs. Now if I put the value of s, then for limit s tends to 0, this value will be 0, plus I can take the limit here, limit s tends to 0, s gs. Now this limit s tends to 0 s gs, this term we can take it as kv, because finally we will get a constant term, so that we can take it as kv. Now when we are taking input as ramp, then we call this coefficient as velocity error coefficient. These names of the coefficients are very important, directly questions are asked mentioning these names, so you have to remember for which name stands for which coefficient. So directly you can solve the formula taking limit s tends to 0 sgs, or previously limit s tends to 0 gs, that was kp, means position error coefficient. Now limit s tends to 0 sgs, that is velocity error coefficient. So I am writing it here, limit s tends to 0 sgs, that is kv, is equal to velocity error coefficient. Velocity, previously it was for unit step position, it is velocity error coefficient. So this was all about for unit ramp. Now the third, that is for unit parabolic input. For unit parabolic input, obviously rs means the input will be 1 by s cube for parabolic. So in this case ess will be limit s tends to 0 s into 1 by s cube by 1 plus gs. gs can be anything, means the open loop transfer function, as we are taking unity feedback, negative unity feedback system. So here it will be limit s tends to 0 1 by s square plus s square gs, just like the previous method. So in this case similarly it will be 0 plus limit s tends to 0 s square gs. Now this can also be written as 1 by ka, where this ka is actually limit s tends to 0 s square gs is equal to acceleration error coefficient. So now the name is acceleration. So for unit step it was position error coefficient kp, for unit ramp it is kv, that is velocity error coefficient, for unit parabolic input it is acceleration error coefficient. Just remember the names and you can directly solve the problems. Now we have to understand about the general expression of any system transfer function. So general expression of any system transfer function, obviously it will be a k, a constant term, we can take it because any constant term can be coming out from the expression of s. So a constant term into s plus z1 z2 up to zn, means these are all open loop zeros, divided by s to the power n. Now s to the power n actually tells us about the number of poles at the origin, means at the origin means at 0. So obviously that will be denoted by s to the power n. N is the number of zeros at the origin. Now rest is s plus p1 p2 up to pn, means this much poles can be there, n can be anything. Depending on this n value, means this s to the power n value, we call it system type. Means if the value of n is equal to 0, means there is no poles at origin, so that system is called type 0 system. If n is equal to 1, then type 1, and if n is equal to 2, then type 2 system. For this much system, we actually consider the steady state error, and we find out the steady state errors for this system, because if we talk about any higher type of system, it can be like we get them from these expressions. I have written the expressions here, means n is equal to 0, n is equal to 1, and n is equal to 2. N is actually the number of poles at origin. So now we have to find out the steady state error expressions for these three type of systems. Now for first type 0 system we are taking. For unit step input, we know Kp is equal to limit s tends to 0 gs. Now for type 0 system, this gs value will be k into s plus z1, s plus z2, like this, s plus zn, divided by s to the power 0, s plus p1, s plus p2, like this, s plus pn, and it will be limit s tends to 0. So this term will become 1, this is constant, and all the s terms will be 0. So the finally it will be k into z1, z2 up to zn by p1, p2 up to pn. We can take it just an constant. So finally the steady state error, if we put this kp value in steady state error expression, it will be 1 by 1 plus k. This is the final expression for steady state error for unit step input of an type 0 system. Now similarly for unit ramp, for unit ramp input we know limit s tends to 0 sgs, that is kp. Now if we put sgs, s, this is, remember this is s, this is multiplied, this is this s, and the gs is k, s plus z1 up to s plus zn, and here it is s to the power 0, means this is nothing but 1. So I am directly writing it as 1 into s plus p1 up to s plus pn, and here it is limit s tends to 0. So there is no s term to cancel this s term, so if I put the value tends to 0, it will be totally 0. So in this case, for unit ramp input, the steady state error expression, that will be 1 by kv, previously we have done. So it is 1 by 0, so it is infinite. This is infinite, obviously. Similarly, if we do for unit parabolic, parabolic input, the k term, that is limit s tends to s square gs for type 0 system. If sgs is 0, obviously k s square gs, this will finally result into 0. So in that case, steady state error will be one more time 1 by 0 is equal to infinite. This is for unit parabolic input. Now type 0 system is done. Now type 2 system. Type 2 system will be doing in the similar process. for unit step input, in this case kp will be limit extends to 0, but the difference is in gs term there will be one s term in the denominator. So when we put s tends to 0, this whole term will become infinite, and when we put that in steady state error expression, that is for unit step input 1 by 1 plus infinite, the whole term will become 0. That is for unit step input. Now these are two for unit ramp input and one is for unit parabolic input. For unit ramp input, steady state error will be 1 by k, and for unit parabolic input, steady state error will be infinite. These are all for type 1 system. So if you want the derivation, you can pause the video and see it. This is just nothing but the previous ones. So previously for type 1 system, the steady state error for unit step input was 0, but for unit ramp it was 1 by k. Here for unit ramp it will be one more time 1 by infinite is equal to 0. Only the parabolic, for parabolic input, that is ka, is limit extends to 0, s square gs. In gs, in the denominator it is s square 2. For type 2, in the origin there are 2 poles. S square term will be cancelled. So this whole term is actually we are taking as k. So steady state error will be 1 by k is equal to 1 by k. So now I am summarizing the whole thing, just listen it very carefully. That is, for unit step input, the type 1, for type 0 system, the steady state error is 1 by 1 plus k. For type 1 unit step input, the response will be, means the steady state error will be 0. For type 2, the steady state error will be 0. Now we are taking unit ramp input. In that case, for type 0 system, steady state error will be infinite. For type 1 it is 1 by k. For type 2 it is 0. Now for parabolic input, type 0 systems steady state error is infinite. Type 1 steady state error, for type 1 steady state error is infinite. For type 2 it is 1 by k. So here all the expressions of steady state error ends, and this was the very vital and important topic. So if you like the video, please share and subscribe and follow my all the videos, so it will be very helpful for you. Thank you.